and we are going to present our dataset, UG2, a video benchmark. Aerial videos are a key component in a number of applications, such as scene recognition, robotic navigation. However, these videos are quite different from the images or videos we find in the internet today, due to a large number of imaging artifacts, such as motion blur, lens glare, etc. When it comes to recognition algorithms, they don't map well to these kinds of videos, and the classification accuracy is very low. Ideally, methods from computational photography should improve the results by removing noise or by making these videos look pretty. In order to analyze these effects, we introduce our dataset UG2. Our dataset consists of 3 collections, out of which 2 contain aerial videos. There are about 289 videos, and our collections are UAV, which consist of Creative Commons tagged YouTube videos, glider videos, and a controlled collection taken at Notre Dame. There are about 158,000 annotated frames with objects in them, and there are about 37 ImageNet classes. Here are some of the examples from our collection, and as you can see, they are quite different. If you squint your eyes, you might be able to see some puddles in the ground collection. Moving on, for our baseline classification algorithms, we use the following pre-trained networks. And since our dataset contains high variability of both object scale and rotation, it is very difficult for us to do fine-grained ImageNet categories. And that's the reason why we introduced the concept of superclasses. As for example, all these images here contain an instance of car, but since, the distance of the camera from the ground is huge, it's utterly difficult for us to know whether that car is a sedan or a limousine or a jeep.
To take into account for this, we introduced the concept of superclasses, and we defined 2 classification metrics. The first one is the rate of detection of at least one correctly classified scene-set class in the top 5 predictions, and the second one is the rate of detection of all possible scene-set classes. In here we can see some of our baseline classification results. In the y-axis we have the second metric, and in the x-axis we have the first one. As we can see, there is a sharp difference between the results of the ground collection to that of the other 2 collections. This is mainly because even though the ground collection images do have a lot of artifacts, their image quality is still way higher in comparison to the other 2 collections. However, it's important to note that none of the collections achieve a classification rate higher than 60%. We then proceeded to evaluate the impact of enhancement algorithms on classification. Mainly, we evaluated 2 kinds of algorithms, resolution enhancement and deblurring ones. Here are some of our experimental results. As we can see in red, it's our baseline classification, and most of the algorithms were able to actually improve the classification rate in at least one of the 2 metrics. However, there are still some algorithms that decrease the classification rate, and even the algorithms that increased it, they only increased it by at most 2%. We observed a similar behavior for the ground collection. However, the number of algorithms that decreased the classification rate was higher. This again might be because the quality of the images in this collection is way higher, and some of these algorithms may be biased towards images with a lot of artifacts in them. And finally, we also analyzed the impact of weather conditions. We found out that rainy weather proved to be the worst for classification tasks, while cloudy weather proved to be a better environment for this kind of challenges. Additionally, we didn't find any impact on the enhancement algorithms that we tested on removing these weather condition artifacts. As we can see, there is still much research to be done in terms of both the pre-processing algorithms and the classification algorithms. That's why we introduced to you the following challenge.
I think Chris did a great job in introducing our challenge. We are holding this UG2 prize challenge at CVPR 2018, where a total of $75,000 can be won in prizes. For more details, please visit our website or scan the QR code. And we would like to thank our sponsors, IARPA, for the research and also for organizing this workshop. And if you have any questions about our dataset or our prize challenge, please visit poster number 3B5. Thanks.